Welcome, dear children, to today's topic, capacitors and capacitance. Capacitors is a device used to store electric charge and electrical energy. And basically, a capacitor consists of two conducting objects separated by some distance. And there can be either air or any dielectric medium between the two conductors. So, capacitor is a system of two conducting objects separated by a dielectric medium or air. That's what we mean by a capacitor. And these capacitors have got wide uses in our daily life. So this diagram shows the basic structure of a capacitor. We have two conductors, and these two conductors, they store equal charges. Okay. This diagram shows a most common capacitor called parallel plate capacitor. In this case, the two conductors are two conducting plates separated by a dielectric medium or air. When the capacitor is connected to a battery, the capacitor plates or conductors, they get charged. As I said earlier, one will get charged positively and the other will get charged negatively. The potential difference between the two will be equal to the potential difference provided by the battery, which is used to charge the capacitor. So if the battery voltage is increased, the amount of charges stored in the plates also increase. That means the charge stored on the plates or the conductors is directly proportional to the potential difference between the plates. Or we can write Q is equal to a constant of proportionality C into V. This constant of proportionality is called as capacitance. So, the capacitance of a capacitor is defined as the ratio of magnitude of charge on either of the conductor plates to the potential difference existing between the conductors, or C is equal to Q by V. And the SI unit of capacitance will be coulomb per volt, or it is farad. And this farad is a very large unit of capacitance, and in practice we use smaller values of units, that is 1 microfarad, which is 10 raised to minus 6 farad, 1 picofarad, which is 10 raised to minus 12 farad, etc. And the symbol of the capacitor is as shown. One more important point to be noted about the capacitor: the total charge stored in the capacitor will be equal to 0, because one conductor stores a charge plus Q and the other conductor stores a charge minus Q. So the total charge stored will be equal to 0. When we say capacitor stores charges, it means that amount of charge which is stored in any one of the plates. Okay, and in our daily life, there are different types of capacitors which are available. They are of different shapes: cylindrical shape, disc shape, small ones also available. Electrolytic capacitors are there, and depending on the nature of the dielectric which we use, that means in the gap between the two conductors we use a dielectric medium. So depending on the nature of that dielectric medium, also the capacitors are of different types, called ceramic capacitors, electrolytic capacitors, paper capacitors. Like that, different types of capacitors are used. Now, in that above equation, that is C equal to Q by V. In that equation, for C to be very large, V will be small for a given Q, isn't it? if Q is constant, we are assuming Q to be constant, for capacitance to be large, V will be small. Got it? That means a capacitor of large capacitance can hold large amount of charge with very small V. And this is what we expect. That is, a good capacitor should be able to store large amount of charge without much increase in potential, or the potential difference between the two conductors should be very small. Okay, if it is not so, we just imagine the potential difference is very high. Instead of small potential difference, if the potential difference is very high, it means that a very strong electric field will be produced around the conductors. If the potential difference is high between the two plates, then the electric field around the plates also will be very high. A strong electric field, it can ionize the surrounding air and it can accelerate the charges, because we know naturally air or dielectric medium, they do not conduct electricity. But if the electric field is very high, this ions, that means the air or the dielectric between the two plates gets ionized and they start conducting. In that way, the charges stored on the capacitor plates will decrease. Are you getting what I am telling? Naturally, the capacitor plates are separated by a dielectric medium or air. Whether it is dielectric medium or air, it is non-conducting. But in case very strong electric field is produced, which is caused by very high potential difference between the two plates, in that case, this dielectric medium or air starts conducting. If it starts conducting, what will be the case? The charges gets neutralized. That means that way the charge on the capacitor plates starts decreasing. So in that way, the capacitance or the charge stored will be less. So in order to avoid such situation, we should choose large, in order to store big charges, large amount of charges, we should use large value capacitors. What is the advantage of large value capacitors? It will store large amount of charge with very small potential difference. This is what is happening during lightning also. So during lightning, before lightning, actually what is happening when the clouds are in motion, the charge on the clouds will be increasing due to rubbing and all. Okay, when they rub against each other, the clouds, when they rub against each other, the charges on the clouds increases. Okay, when the charge stored on the clouds increases, the potential difference and hence the electric field between the cloud and ground increases. Electric field also increases, and in such a case, the air starts conducting and sudden electric discharge takes place between the cloud and the earth. And that's what we see as lightning. Okay, so the thing is this, that is, for all dielectric media, including air, there is a maximum value of the electric field which it can withstand without losing its insulating property or without the breakdown of its insulating property. And that maximum value of electric field which it can withstand is called as dielectric strength. So dielectric strength is the maximum electric field which a dielectric medium can withstand without breakdown of its insulating property. Okay, and for air, that value is 3 into 10 raised to 6 volt per meter. So thus, for a capacitor to store large amount of charge without leaking, its capacitance should be very high so that the potential difference and hence the electric field do not exceed the breakdown limits. Okay. Or in other words, we can say that there is a limit to the amount of charge that can be stored on a given capacitor without significant leaking. This picture shows various capacitors which are available. They are available in different shapes. Okay. And the lower diagram shows the different symbols used to represent a capacitor. First one is the usual notation which we also use. Sometimes that second one also, polarized capacitor, that type of diagram also we used to see. The last one stands for a variable capacitor. That means its capacitance what varies. Now we are going to find the expression for capacitance of a parallel plate capacitor. So the diagram shows a parallel plate capacitor which consists of two conducting plates of same area and same dimensions separated by a distance d, and the charge densities of the conducting plates, we are assuming it to be sigma. So the upper plate is having a surface charge density plus sigma, and the lower plate is having a surface charge density minus sigma. So since we have charged plates, in between the plates there will be an electric field. Okay, and outside the plates also we will find the electric field. That's what we are going to do now. So once again, the plates have the area A and the separation between the two plates is D. The two plates are of same area and same length and all, and both of them have the same surface charge density plus sigma and minus sigma. Now we will find the electric field on either side of the two plates and in between the plates. So this diagram shows the electric field due to the two charged plates in the three regions. So the thing is this, here we assume these plates to be of infinitely long plane sheet of charge. But here actually the sheets are of constant or finite area and length. Then what makes us to assume this? It is this condition, that is d square is very much less than a. This is our assumption. This is a very important assumption. That means the separation between the two plates is very much less than the other dimensions of the plates, or the condition is d square is very much less than a. Under this condition, we can assume these two charged plates to be infinite plane sheet of charge. And we know electric field produced by an infinite plane sheet of charge is sigma by 2 epsilon 0, and its direction will be directed outwards for positive charge distribution and directed inwards for negative charge distribution. So here we consider three regions. First one is this, that is on the upper side of the positive plate. Second one is on the lower side of the negative plate, and the third is in between the plates. So when we calculate the field in region 1, we will get, that means due to positive charge the field will be in the upward direction, and due to negative charge field will be in the downward direction, and both the plates are of same surface charge density, so both field will be of same value sigma by 2 epsilon 0. Since they are in opposite direction, the two fields get cancelled, giving a result 0. That means on the upper side of the positive plate the electric field is 0. Similarly, in the second region, that means on the lower side of this negative plate, also we will get the field to be equal to 0. Now, looking at the field in between, positive plate and the negative plate produces electric field in the same direction. So, those two fields will get cancelled, giving a net electric field sigma by epsilon 0. Okay, and the direction of that electric field will be from positive plate to negative plate. So this diagram shows the electric field due to the two charged sheets. Okay, so this condition don't forget. Now we got the expression for the electric field between the two plates. Now we find the capacitance. To find the capacitance, the equation which we use is C equal to Q by V. So in order to use that equation, we need to get V. So how to get that V? We already know the equation E is equal to delta V by delta L. One negative sign is there, but dealing with the magnitude, no need of considering that negative sign. For a uniform electric field, we can write E is equal to V by D. So here, the thing is this, between the two capacitor plates, there is a field. That field is uniform electric field. And what is that? How much is that uniform electric field? Sigma by epsilon 0. So for uniform electric field, we can use this equation. E is equal to V by D, where D is the separation between the two capacitor plates. So V is equal to ED and V is equal to Q by A epsilon 0 into D. Okay, now substitute this V in the expression for C, because we know C is equal to Q by V. Substituting for this V, we will get the expression for capacitance as epsilon 0 A by D. So, see, even if the definition is Q by V, see, actually the capacitance is independent of Q and V, and it depends only on A and D, and of course on epsilon 0 also. So, on what all factors this capacitance depends? It depends on the nature of the medium, that is shown by epsilon 0, and A, what is A? Area of the plates, and D is the distance between the two plates. So this capacitance depends only on the geometry of the system. It is independent of Q and V. Okay. So we usually say that farad is a bigger unit of capacitance. To show that, here we have a calculation. Let's assume we need to make a capacitor whose capacitance is 1 farad, and we keep the distance between the two plates as 1 centimeter. And let's see what is the area of plates required. So from this equation, we get A is equal to CD by epsilon 0, which is equal to 1 into 10 raised to minus 2. 1 centimeter is converted to meter, divided by epsilon 0. So we'll get it around 10 raised to 9 meter square. So area of the plates required is 10 raised to 9 meter square, which implies 30 kilometer length and breadth. So you can imagine how long it will be. So from that, again we can conclude that this farad is a bigger unit of capacitance, and hence we use smaller units like nanofarad, picofarad, etc. See, while deriving the expression for capacitance of a parallel plate capacitor, we assumed the plates to be infinite, but actually the plates are of finite area, length, breadth, etc. Okay, for infinite sized sheets, the field can be assumed to be uniform in between the plates, but in the case of finite plates, the field need not be uniform. That difference in field is given like this. That means towards the end of the plates, the field lines, they bend outwards, and this bending is called as fringing of electric field. Okay, but in the condition, that is d square very much less than a, we can assume that what plates to be of infinite size. That's how we use that equation sigma by 2 epsilon 0 to obtain the field between the two capacitor plates. So this point fringing field is to be noted. So only this much for today. Thank you.